In other words, if yt is a semi-Markov process, then the process at y of t plus tn is independent of. A semi-Markov process is thus a stochastic process in which changes of state occur according to a Markov chain and in which the time interval between two successive transitions is a random variable whose distribution may depend on the state from which the transition takes place as well as on the state to which the next transition takes place. Y of t. Y of t plus Tn is independent of y of t given the complete past history y of t and xn is equal to I and is identical to the process y of t given x naught is equal to I because of time homogeneity. Not only y of t plus Tn is independent of y of t, it is also identical to the process y of t given x naught is equal to I because of time homogeneity. It is satisfying the time invariant property also. So, it is very important when the Markov property is satisfied at the time in transition time instance Tn, then the stochastic process is called a semi-Markov process. Thus, in a semi-Markov process, the Markov property is satisfied only at the each of the transition epochs and not at all times. This is very important. The Markov property is satisfied only at the each of the transition epochs Tn, not at all the times. If the Markov property is satisfied at all times, then the stochastic process is called the Markov process. Since it satisfies only at each of the time transition instance, the Markov process is called a semi-Markov process. The fact that the Markov property holds at each of the transition epochs Tn of the stochastic process y of t entails the Markov property also holds for xn. Since xn is nothing but the y of Tn, therefore, the Markov property is satisfied for the stochastic process xn, not for the Markov property is satisfied for the y of t for all times. Hence, xn turns out to be the time homogeneous embedded Markov chain with the state space omega. Y of t is a stochastic process and x of n is nothing but the y of Tn, where Tn is the transition time instance, and the Markov property is satisfied only at all the transition time instance. Therefore, xn form a discrete time Markov chain. Since xn is y of Tn, this xn stochastic process is called a embedded Markov chain. Xn stochastic process is embedded in the stochastic process y of t. Therefore, xn is a time homogeneous embedded Markov chain because it satisfies the time invariant property as well as the Markov property. Therefore, xn is the time homogeneous embedded discrete time Markov chain. Now, we can say x of n comma t of n constitute a Markov renewal process or semi-Markov process with the state space omega. xn is a embedded Markov chain where xn is y of Tn and the Tn is nothing but the transition time instance. Therefore, the together xn comma yn constitutes Markov renewal process because these are all the time points in which the system is moving into the different states, and the Markov property is satisfied only at those time points. Therefore, it is called the semi-Markov process or Markov renewal process with the state space omega. The stochastic process The stochastic process y of t is not a Markov process, although it inherits some important properties of Markov processes. The associated process, that is x of n, is a Markov process. Hence, the name xn comma tn as a semi-Markov process. In conclusion, a continuous time stochastic process in which the embedded jump chain, that is nothing but the discrete process registered what values the process takes. So, the embedded jump chain is a Markov chain In conclusion, a continuous time stochastic process which embedded has a Markov chain and where the holding times are random variables with any general distribution whose distribution function may depend on the two states between which the move is made, we say it is semi-Markov process or Markov renewal process. Whenever these properties are satisfied, we say the stochastic process is a semi-Markov process or Markov renewal process. The semi-Markov processes are non-Poissonian with the renewal property. This means that the probability of a jump from a state I to j at a certain time depends only on the states I comma j and the time t since the last jump occurred. If you restrict the holding times or exponential distribution and each time transition instance or the renewals, then the special case of the semi-Markov process is a Poisson process. But in general, semi-Markov processes are non-Poissonian. If you make assumptions of holding times or exponential distribution with the same parameter and each time transitions are nothing but the renewals, then the special case of semi-Markov process is the Poisson process. A semi-Markov process where all the holding times are exponential distribution is called a continuous time Markov chain. So, if I restrict only the holding times are exponential distribution, the each transition need not be the renewals, then a semi-Markov process is a continuous time Markov chain. Now, we are going to discuss the steady state measures of semi-Markov process. The analysis of a semi-Markov process is performed in two stages. In the first stage, the semi-Markov process stays in a state I for some random amount of time. For example, in the sample path of a semi-Markov process, in this model we have a 4-state semi-Markov process. So, in each state the system stays a random amount of time. Let us consider that the time spent in state I follow a general distribution with the distribution function hi of t. That means, in this example h1 of t, that is the time spent in this system spent in the state 1. h2 of t is the distribution of the system staying in the state 2 and so on. In the second stage, the SMP moves from the state I to j with the probability pi comma j, where pij is defined. What is the probability that the system was in the state I at the nth time instance the system will be in the state j at the n plus 1th time instant, I comma j belonging to omega. So that is a conditional probability. The conditional probability of p x n plus 1 is equal to j given x n is equal to I for I comma j belonging to omega. So the SMP can now be completely described by the vector of Sojourn time distributions h of t and the transition probability matrix P, that is P of I comma j. So the transition probability matrix is the transition probability, therefore all the row sums are equal to be 1 and the values are lies between 0 to 1, and you have to supply the Sojourn time distribution for each state. So if these two informations are given, then we are known with semi-Markov process. To compute the steady state probability vector, let us assume that pi is the vector, pi 1, pi 2 are the elements of a semi-Markov process. First calculate the mean sojourn time, that is nothing but the small hi. Since hi of t is the distribution function, so 1 minus hi of t, the integration between 0 to infinity, will be the mean sojourn time, because each random variable is a non-negative random variable, therefore the mean will be 0 to infinity 1 minus the CDF integration for each state I. Next find the steady state probability vector Vi's for the embedded Markov chain of the semi-Markov process. First we have to find out the steady state probability vector for the embedded Markov chain of the semi-Markov process, and using the steady state probability vector and the mean sojourn time, you can get this steady state probability vector of pi. So how to find the steady state probability vector of embedded Markov chain? So you know P is the transition probability matrix. So solve V is equal to Vp and summation of Vi is equal to 1, you will get Vi's. The V is equal to Vp is a homogeneous equation, and including summation of Vi is equal to 1, you will have a non-homogeneous system of equation. So you can get the non-trivial solutions satisfying these two conditions. So once you know the Vi's, you can compute the steady state probabilities of the semi-Markov process, that is nothing but Vi's multiplied by Hi's divided by summation of all the Vj's Hj's, where j is belonging to omega. So the Vi's are nothing but the steady state probability vector of embedded Markov chain, and Hi's are nothing but the mean sojourn time, and pi i's you will get by using this formula. Now let us consider the simple example, the stochastic process with the state space omega 1, 2, 3, 4. In the previous steady state measures, with the assumption that the steady state probability vector probabilities exist, we are giving the how to compute the steady state probability measures. So here the assumption is that steady state probabilities are exist. Now we come to the example. So this is a 4-state stochastic process with the states 1, 2, 3, 4, and H's are nothing but the CDF of sojourn time in each state, and xn is nothing but y of tn, and xn comma tn will form a Markov renewal process or semi-Markov process. Assume that the time spent in the states 1 and 2 follow exponential distributions with the CDF h1 and h2. Whereas the time spent in the states 3 and 4 follow uniform distribution with the CDF H3 of t and H4 of t. So, the sojourn time in the state 3 is uniformly distributed between the intervals 1 and 2, and the sojourn time spent in the state 4 is also uniform distribution between the intervals 2 and 3. Therefore, the CDFs are in this form H3 of t and H4 of t. The semi-Markov process moves from the state I to j with the probability Pi of j, that is nothing but the transition probability matrix can be in the form the states are 1, 2, 3, 4. Therefore, in the one step transition probability of system is moving from 1 to the state 2 is sure, therefore that probability is 1 and all other probabilities are zeros. Similarly, the system moved from the state 2 to 3, that probability will be 1 and all other states moving probabilities are 0. Therefore, all other transition probabilities from the state 2 to 1, 2 to 4 are 0, whereas the 2 to 3 will be 1. Similarly, 3 to 4 will be 1 and all other states, all other transition probabilities are zeros. Then the system moving from the state 4 to 1 is 1 and all other states are 0. So, you know the transition probability matrix as well as you know the the sojourn time distribution. So, using the transition probability matrix, by solving you can get the steady state probability vector of embedded Markov chain. If you see the transition probability matrix, since it is a transition probability matrix, the values are lies between 0 to 1 and the row sum is 1. But in this particular transition probability matrix, it satisfies the one more additional condition, the column sum is also 1. Therefore, if you solve the V is equal to Vp and the summation of Va is equal to 1, the solution will be 1 divided by the number of states. So, the steady state probabilities are uniformly distributed, uniform distribution. So, number of states are 4, therefore, the steady state probability of the embedded Markov chain is 1 by 4. So, you know the steady state probabilities of embedded Markov chain, and from the sojourn time distribution you can find out the mean sojourn time. Since the first two random variables first two states sojourn times are exponential distribution, therefore, the mean sojourn time is 1 by 2, 1 by 3 respectively for the states 1 and 2. And the sojourn time in the state 3 is uniform distribution between the interval 1 to 2. Therefore, the mean sojourn time is 3 by 2. And for the state 4, the sojourn time distribution is uniform distribution between the intervals 2 to 3. Therefore, the mean sojourn time is 5 by 2. So, using transition probability, using the steady state probabilities of embedded Markov chain and the mean sojourn time, using the steady state probabilities of embedded Markov chain and the mean sojourn times, you can get the steady state probabilities of semi-Markov process.